Hi there, welcome to this Elkchemist chemistry video looking at the extraction of metals. In this video we're going to talk about how the reactivity series shown here underpins which method is most suitable for extracting particular metals from their ores based upon their reactivity. So this is a small section of the reactivity series running from potassium as our most reactive metal to platinum as our least reactive metal in this slice of the full reactivity series. This arrow on the left hand side is increasing reactivity. I've thrown in carbon and hydrogen as non-metal examples of agents we could use to extract certain metals from ores. We're going to focus in particular on carbon today, later in the video. Okay, so I use that term ore, O-R-E. Now you may already have an idea about what an ore is from popular culture, specifically games like Minecraft, where it might conjure up the image of a cubic block of earth containing the particular materials you need to craft something in the game. Now, that's not a million miles away from what an ore really is. Ores are rock deposits which contain metal compounds in sufficient proportions to make it worth extracting the metal from the metal compounds found within that rock deposit. However, some metals aren't extracted from ores, metal compounds found within the Earth's crust. Some are found as pure metals in the ground or in riverbeds. Things like this. That's my cartoon picture of a gold nugget. So why is gold and silver and platinum found as pure metals rather than as metal ores? It's all to do with their position in the reactivity series. Metals like silver, gold and platinum are found near the bottom of our reactivity series. They are low reactivity metals that are unreactive in nature. They do not react with oxygen found in our atmosphere to form oxides, which are the main compounds that are found in ores. Instead, they are found native as pure metals in the ground itself. That could be as nuggets or as seams of the pure metal found underground. Now, looking at the gold nugget makes you think of a period of history which is both famous and infamous involving gold, and that's the 1849 California gold rush. So in 1848, America has gained California as a territory from Mexico in the American-Mexico War, and a prospector at the base of the Sierra Nevada mountains in a river found flakes of gold, and that caused a sudden rush of prospectors from the eastern seaboard to the west, to California, to mine for gold. Now, unfortunately, that caused a lot of violence, both amongst those prospectors, but also against the indigenous Indian population. And it just shows you that, unfortunately, the desire for wealth and the association of value with gold has both useful applications, but also a much darker history, which we should all be mindful of when it comes to using wealth appropriately. Right, after that detour, back to the chemistry. The metals in red below carbon are reactive enough to form compounds and therefore be found as ores. That could be oxides or other compounds. But they are less reactive than carbon, and therefore we can use carbon as the key extracting agent. So metals below carbon in the reactivity series are extracted by a reaction known as reduction by heating with carbon. The reason we use carbon and not more reactive metals higher up the reactivity series is because carbon is very cheap in comparison to these metals, which are extracted through different processes I'll talk about later, which adds to their expense. Now, I just want to expand upon that reduction of carbon idea with a simple example. We're going to look at the extraction of lead from lead oxide by using carbon as a reducing agent. Let's first of all focus on what's happened to the lead oxide in this reaction. So the lead oxide has been reduced to form lead on the other side of the reaction. How do we know that the lead oxide has been reduced? Well, there are lots of ways we look at this. We could look at it in the idea of the lead oxide losing oxygen atoms and defining reduction as the loss of oxygen atoms from a chemical species in a reaction. We could also use the oil rig mnemonic to consider reduction in a different way. Oxidation is loss of electrons. Reduction is defined as the gaining of electrons by a chemical species across the course of a chemical reaction. Now, the lead inside lead oxide is not comprised of lead atoms, but it's comprised of lead ions, because lead oxide is an ionic compound. So these are lead ions. So lead ions have the charge 2+, Pb2+. Now, on the other side of the reaction, they have formed metallic lead atoms as part of a giant metallic structure. So we went from lead ions on the left-hand side of the reaction to lead atoms on the right-hand side. Now, the only way that can happen is if the lead ions have been transformed into lead atoms. They've become uncharged overall. And that means they must have gained electrons across the course of this chemical reaction to become uncharged lead atoms found within our giant metallic structure. So Pb2 plus 2e minus goes to Pb is an ionic half equation showing what's happening from this side of the equation to this side as lead ions in lead oxide are reacting with the carbon to form lead atoms, having gained electrons across the course of that chemical reaction. Now let's look at carbon to understand why it's defined as being a reducing agent. Reducing agents are themselves oxidized across the course of the chemical reaction taking place. So how do we know the carbon has been oxidized in this reaction? Well, looking at it, the carbon has formed carbon dioxide on the right-hand side of this chemical reaction. Therefore, it's gained oxygen atoms. That's a classic definition of an oxidation reaction. We could also look at it in terms of its oxidation state. So carbon has an oxidation state of 0 on the left-hand side as elemental carbon, but it has an oxidation state of +4 in the compound carbon dioxide, because each oxygen has an oxidation state of -2. There are 2 oxygens, that's -2, -2, balanced out by the oxidation state of the carbon being +4. So the fact that the oxidation state of carbon has changed from 0 to +4 is another sign that an oxidation reaction is taking place, because oxidation states can be seen essentially as an accounting system that shows whether a species was losing or gaining electrons across the course of a chemical reaction. It's an accounting system which treats everything as if it's kind of ionic in nature, even though we know that carbon dioxide is actually a covalent molecule in nature. So we can be sure that carbon is a reducing agent because it was the electron donor or donator in this chemical reaction. It was giving its electrons to the lead ions to turn them into lead atoms across the course of the reaction, and that's why carbon is defined as a reducing agent. Okay folks, just before we get on to the most reactive metals and how they're extracted, just want to say, if you find this video useful, please do think about giving it a like, maybe think about subscribing to the channel. You could even ring the bell to keep notified of our latest content. I try and put out videos on a weekly basis, and your support is hugely appreciated and keeps me motivated to move on to the next topic and the next topic and the next topic. You could also think about sharing this content with friends who are studying chemistry to help support their learning as well. My main objective is just to make as many videos as possible and support as many people's learning of chemistry, and to just spread my passion for the subject. So again, thanks so much for your support, and let's finish up this video now. So, metal compounds containing metals above carbon in the reactivity series cannot be extracted using carbon as a reducing agent, because they're more reactive than carbon and they won't react with carbon in that way. And it would be inefficient to extract metals using more reactive metals via displacement reactions, because one, how did you extract those metals in the first place? And secondly, it's quite an expensive and laborious process. There must be another method for extracting metals that are more reactive than carbon from their ores. And there is, and it's known as electrolysis. Electrolysis is defined as a process by which compounds are broken down into their simpler components using an electrical current. I'm not going to expand upon electrolysis in this video because I've already done so in previous videos, and cards should be appearing at this point which you can follow to check out electrolysis in more detail. It's a really important topic, so I would definitely advocate doing so. But I will leave you with a quick story about the expense of the more reactive metals and how it's changed over the years. So, the electrolysis of aluminium oxide to extract aluminium first became viable in the very late 1800s. Before that, aluminium was exceptionally difficult to extract and therefore exceptionally expensive. And there are some interesting stories that come out of that. Napoleon III, the Emperor of France in the 1850s to the 1870s, would reserve his aluminium cutlery for his very best guests and his gold and silver cutlery for his lesser guests, because aluminium was so expensive at the time, whereas now it's a commonplace material. Also, the Washington Memorial had a cap of aluminium placed at the very top because at the time of its creation, aluminium was the most expensive metal available, and therefore it was a statement of America's power and prowess at the time. Unbeknownst to the American people, after 1890, aluminium became a lot easier to extract for electrolysis and its value plummeted, making the tip of the Washington Memorial much less valuable in the modern age than it was when first constructed. The value of hindsight. I really hope you enjoyed the video, guys. It was awesome talking to you, and I'll see you in the next one. Take care. Bye now.